What is the future of space travel? The use of chemical-based rockets to leave our planet and explore space may very well be a dead-end technology. It's old, outdated, and it's extremely inefficient. Surely we've discovered or improved upon newer, more efficient technology in these last 60 years, right? The answer to that is yes, and we're going to go over them in detail. We will explore exotic technology that includes using solar wind to sail amongst the stars, using nuclear bombs to approach light speed, and even dabbling with technology that exploits loopholes in the laws of physics which NASA has recently been experimenting with. What's wrong with chemical rockets? Chemical rockets may be a dead end because of their extreme inefficiency. Just to put the space shuttle into Earth orbit to reach 17,500 mph, the rockets need to carry 15 times its weight in fuel, and that's considered extremely efficient among other chemical-based rocket systems. To escape Earth's gravitational pull and explore our solar system to reach 25,000 mph, you would need significantly more fuel. Space shuttle occasionally. Space agencies can mitigate some of the problems by using gravitational assists from planets. They use a planet's gravity well to slingshot a probe toward its destination, significantly speeding it up. The problem with this solution is one of availability. To take advantage of a planet's gravity well, the planet has to be in a specific place at a specific time. This leaves a small window which a probe would need to be launched. Some of these windows can be incredibly rare. The Voyager space probes, which explored the planets in the outer solar system, took advantage of a planet alignment that happens only once every 176 years. Then there is the cost. The average cost to put the space shuttle into orbit is $450 million per mission. That's a huge price tag just to reach low Earth orbit, and it's also a big part of the reason the shuttle program was scrapped. If we wanted to leave Earth orbit and explore our solar system with such an inefficient technology, without gravitational assists, the problems become severely compounded. Because there aren't any fuel stations in space, a spaceship has to carry all its fuel with it. Fuel which is not only pricey, but heavy. If we wanted to leave our solar system and travel to our closest neighboring star in a reasonable time frame, say 900 years, using standard chemical-based rockets, it would require 10,137 kilograms of fuel. That is more fuel than exists on our planet. Thus, we need to look towards developing a better, more efficient method of propulsion. Solar sails. Solar sails do exactly as the name suggests. They sail on the solar wind. There is no actual wind in space because space is a vacuum, but there is something similar that a spacecraft could use to propel itself. A craft equipped with a giant sail made out of ultra-thin mirrors can harness a combination of light and high-speed ejected gases from the sun to reach incredible speeds. Solar sail. Japan. Japanese Icarus solar sail. The pressure of the light and gases is very small, but since there's no friction in the vacuum of space, it allows that small pressure to build up over time. Given enough time, this pressure can propel a craft to a significant fraction of light speed. The time to reach top speeds could be lessened by aiming extremely powerful lasers or masers at the sails from a base on the moon or other satellite without an atmosphere. However, a solar sail does have its drawbacks. Once far enough away from the sun and any laser boosting stations we have set up, the craft would no longer be accelerating and instead rely on its own inertia to travel to its destination. The craft would then have to direct its sails towards the destination star to decelerate and slow down. Solar sail spacecrafts became a reality when, back in May 2010, the Japanese launched the Icarus probe. It successfully deployed its solar sails and is currently in a wide orbit around the Sun. It's expected to reach Jupiter in a few years. Ion drive. An ion thruster or ion drive is a lot less exciting than how it is often portrayed in science fiction books and movies. It operates on similar principle as the solar sail, using very low thrust, but over an extended period of time. It achieves this thrust by ejecting charged ions, gas, or plasma out of its electric engine which propels the spacecraft. This method of acceleration allows a craft to achieve a very high specific impulse. Such a craft would only work in the vacuum of space since the thrust is so low. However, the fuel required by the engine is significantly less than is required by chemical rockets, which maxes out thanks to the Carnot limit on efficiency. This technology is being heavily considered for future space missions and has already proven its feasibility in space. In 1998, NASA launched the Deep Space One probe, which was powered by a xenon gas ion engine, and was the first ion drive in space. In 2003, Japan launched the Hayabusa probe, which used 4 xenon ion engines. Its mission was to rendezvous with an asteroid and collect samples. It completed its mission and returned to Earth in June of 2010. Like the solar sail, ion drives also have their drawbacks. First, they would need to carry their fuel with them. While the amount required to get the nearest star is technically feasible, it wouldn't be very practical. Travel time is another issue. While an ion drive is significantly more efficient than rocket engines and is great for jaunts around our solar system, interstellar travel is another matter entirely. With a gravitational assist from our Sun, it still would take 19,000 years to reach Proxima Centauri with a ship using an ion engine. We need more speed if we want to leave the confines of our solar cradle. Nuclear propulsion. If we wanted to get to our nearest neighboring star using the best technology available to us right now, nuclear propulsion is our best option. It's fast, proven, and relatively cheap. A ship equipped with nuclear pulse propulsion and could theoretically reach 12% the speed of light. That is so fast, you could travel completely around the Earth and end up back at your starting point in just under 2 seconds. Or you could travel to the Moon in 13 seconds. It took Apollo 11 4 days to reach the Moon. By comparison, while it would take 19,000 years to reach Proxima Centauri with an ion drive, it would take a relatively manageable 35 years using nuclear pulse propulsion. A human would be able to travel to our nearest neighboring star within his or her lifetime, and it could be done with technology that already exists. The way nuclear propulsion works sounds a bit crazy, but it is proven, and it is relatively simple. Small nuclear bombs are dropped out of the back of the spacecraft which detonate. The resulting force from the explosion accelerates the craft. This is done repeatedly until the desired speed has been attained. An incredibly large, reinforced pusher plate would shield the craft from damages and radiation, while dampeners would be used to mitigate the effects of G-force and provide smooth acceleration. The U.S. military began looking into nuclear pulse propulsion back in 1958 under the project name Orion. The project was shelved in 1963 thanks to the Partial Test Ban Treaty, which prevents nuclear devices being detonated in space. The idea wasn't forgotten, however. In 1973, the British Interplanetary Society developed a similar concept called Project Daedalus. Then in 1998, the Nuclear Engineering Department at SU began developing 2 improved versions of the Daedalus design known as Project Acan and Project Aimstar. One of the obvious drawbacks to nuclear pulse propulsion is that you have to carry your fuel with you. This means carrying hundreds or thousands of small nuclear bombs. There is also the problem of ablation of the pusher plate. Repeated exposure to nuclear blasts will cause erosion, if not sprayed with a special oil, before each detonation. Yet another problem is nuclear fallout. This could be averted if a craft is launched from a polar region, or if a craft is launched into space using conventional rockets, then once far enough away, began using its nuclear propulsion. The late Carl Sagan once suggested that nuclear pulse propulsion would be an excellent use for our current stockpiles of nuclear weapons. Nuclear fusion. A spacecraft equipped with a nuclear fusion engine could explore our solar system without the need to carry a large fuel supply thanks to its efficient, long-term acceleration capability. There are 2 ways a fusion engine could work. The first is using the energy created by a fusion reaction to generate electricity. This electricity could be used to superheat plasma, which then would be ejected out the back of the craft, providing thrust. The second method would be more direct. It would use the plasma-based exhaust from the fusion reaction to provide thrust. The drawbacks of a fusion engine are very similar to that of the ion drive. While fusion is a huge improvement over ion drives, it would be very hard to achieve the higher speeds necessary when traveling between stars. Fusion technology is also still in the experimental stage of development. The technology must overcome hurdles with plasma confinement to become viable. Then a reactor would need to be miniaturized to a size manageable for a spacecraft. Currently, experimental laser-based IC reactors are as large as football stadiums and are struggling to break even with power output. Antimatter. Antimatter is the most potent fuel source that we currently know of. It's also the most efficient. Antimatter is, as the name implies, matter which has its charges reversed. When antimatter comes into contact with normal matter, the two annihilate one another in a ferocious blast of pure energy. A piece of antimatter the size of a small coin contains enough energy to propel a fully loaded space shuttle into orbit. Once in orbit, NASA claims that a trip to Mars would only require as little as 10 milligrams worth of antimatter. An engine using antimatter is pretty simple in its operation. A beam of anti-electrons is released into an engine core where it annihilates the surface of a metal plate. This creates a small explosion which propels the craft forward. Another proposed design uses a sail, similar to the solar sail described above. A cloud of antiparticles is released which then reacts explosively with surface of the sail. This reaction can propel the craft to incredible speeds. According to NASA, an antimatter-powered craft would be able to reach speeds up to 70% the speed of light. That means we could reach Proxima Centauri in just under 6 years. The drawbacks of using antimatter are production and containment. Antimatter is a byproduct of atom-smashing tests done at particle accelerators, tests which are very expensive to operate. If we wanted to produce a single gram of antimatter, it would cost over $1 trillion. Containment is also another issue. Since antimatter violently reacts when it comes into contact with normal matter, it would have to be stored in vacuum containers at incredibly low temperatures suspended by strong magnetic fields. This becomes a challenge because anti-electrons-positrons repel each other, often explosively. Some solutions have been proposed. One suggests that by combining positrons with electrons, researchers can create an element called positronium which can theoretically store the anti-electrons indefinitely. Faster than light. Faster than light travel is just the stuff of science fiction, right? After all, didn't Einstein say that the speed of light is the ultimate speed limit? Not necessarily, claim physicists. The devil is in the details. According to physics, there are ways around the universe's ultimate speed limit. These technical loopholes could theoretically and potentially allow us to race a beam of light and win. NASA researchers know that nothing can accelerate faster than the speed of light, but they also know there is no such restriction regarding space itself. Space-time has no such limit on how fast it can move, and it is believed that space-time exceeded the speed of light during the expansion of the Big Bang. Researchers at NASA's Advanced Propulsion Division have been wondering if space-time can make a repeat performance. A warp drive, normally the stuff of science fiction, would travel faster than light by riding on a wave of space-time. It creates this wave by compressing the space-time in front of the ship and expanding the space-time behind it. A ship then sits in the middle of this wave and is propelled through space. Since the ship itself isn't moving and only the space-time around the ship is moving, no laws of physics are broken. At NASA EcoWorks, researchers have begun to attempt to prove the concept of warp drive with lab experiments. There, the researchers set up a mini warp drive called the White-Jude Warp Field Interferometer. The experiment seeks to generate a very tiny instance of a warp field. A warp field that is so small, it is only expected to perturb space-time by 1 part in 10 million. While the results will be underwhelming if successful, it will be existence for proof of concept. The location for the new project is the facility that was built for the Apollo program, the very same one that put astronauts on the moon. The first scientific paper which took warp drives seriously was written in 1994 by Mexican physicist Miguel Alcubierre. Alcubierre's paper called for enormous energies to power his theoretical warp drive, the mass energy equivalent of Jupiter. Harnessing that kind of energy is impractical and virtually impossible, so his paper went largely ignored. In October of 2012, at the 100-year Starship Symposium, NASA researcher Harold White gave a presentation where he announced that he discovered loopholes in the mathematical equations, loopholes which brought down the energy requirements to levels much lower than previously thought. He calculated that by altering the design of the warp engine and the ship itself, he could get the energy requirements down to just a few thousand pounds of mass. This advancement, and others like it, edge warp drives ever further out of the realm of science fiction and closer to reality.
Thanks for watching. Please subscribe Space Facts channel to see more awesome videos.